Shelf. It's on the, if you look at the right-hand picture here on the upper right of Antarctica, you see a little piece called the Antarctic Peninsula, which is the thumb that sticks up towards South America. This ice shelf, the Larsen Ice Shelf, fringes that part of Antarctica. And an ice shelf is a piece of the ice sheet that's essentially gone afloat. It's pushed into the sea due to these dynamic actions of the ice, the fact that the ice creeps, and it's now floating over the ocean. And in the left-hand photo, you see what the Larsen Ice Shelf looked like on January 31, 2002. It looked like it was in pretty good shape. It had some dark spots on the surface, which are melt ponds, because that area of Antarctica is warming faster than the other part of the continent, and it reaches above freezing in the summer. But on the right-hand side, you see that the ice shelf has completely disintegrated. It's literally, it's like dropping a pane of glass, essentially. Only this pane of glass is about 5,000 square kilometers. It's a huge thing. We had no, and it's also, in some places, it was several hundred meters thick. We had no idea that this could happen. We had no idea that in the course of 5 weeks, between January 31st and 5 March, such a big piece of ice could disintegrate. And then one other thing happened, which was a bit of a surprise to most of the ice community. You can see the glaciers fitting between the mountains behind or to the left of the ice shelf. They started to rush towards the sea, rush in glacial terms. They still move glacially, as it said, but they moved relatively fast. They accelerated by factors on the order of 8. And they reached that plateau of high speed and stayed there, so that in some way it appears that the ice shelf, when it was integral on the left, was buttressing or holding back the grounded ice, the ice bedded on land, and once it disintegrated, ice started moving into the sea and adding to sea level rise. That we understand and can calculate neither the fracture process that broke the ice shelf nor the rushing process which allowed the glaciers to then move some ice into the sea. Now, why is this so hard to do? What's the complication? We have all these computers. Why can't they help us? They can to a certain extent, but not enough. The reason is you have to think about what an ice sheet actually, how it forms. It forms because snow forms in the middle of a cold continent. You start getting a big pile of snow. I'm building a cartoon here, and then the weight of that snow, the gravity eventually as it consolidates into ice, pushes the material down the ice and pushes it toward the edge of the continent where the ice is at lower altitudes, so it's warmer and it can start to melt, but it also interacts with the sea, and that's why you have these icebergs forming on the left-hand portion here. And we understand really neither why, or can project numerically neither why the pressure of how the pressure of gravity is converted into fast motion of ice, nor in any detail how the ice interaction with the ocean causes melting, which then stimulates more rushing of ice to the sea, and that melting is part of the reason, by the way, that this collapse occurred. But so we have general notions. It's very hard to turn those into specific predictions. So we can only provide scenarios for ice sheet behavior in the future. We can't really provide reliable projections, which is why the IPCC didn't try. Now, here are 3 other similar or related features, only this time from Greenland instead of Antarctica. The lower right-hand feature is a glacier. There are analogous features on Antarctica, sometimes called ice streams. These are rivers of ice which essentially draw ice out of the interior. These photos were taken by me from during a commercial flight over Greenland from Northern Europe back to the United States. And they actually showed, you can imagine on that glacier, it looks like it's kind of a river flowing and it's sucking the ice out of the middle of the continent. And when it gets down to the sea, you have a feature like the one there on the upper right-hand part, which again is a part of the ice coming off the continent, fragmenting into icebergs. Those are the dynamic or motion processes that we don't understand well. We do understand the melting processes much better. The blue lake there at the lower right is just a feature sitting on the top of the Greenland ice sheet. There's meltwater. We understand better than we do motion how meltwater gets there, but unfortunately it looks like at the current time the dynamic motion of the ice is at least as important as meltwater to explain the loss of ice from Greenland, and in the future it could get relatively even more important. Now, that's complication number 1. Complication number 2 is that we really don't have a good picture of the importance of local effects. The important local effect, and it's complicated, so I'll explain one of them because it's kind of It's interesting and counterintuitive. If you think about an ice sheet forming, a lot of snow falls in the middle of a continent, a big mass of ice builds up that wasn't there before. That mass of ice is high enough and big enough, has enough mass, I should say, to attract the water in the surrounding ocean. It actually pulls the ocean water closer to the continent, say Greenland, than it otherwise would be. So the sea level is naturally somewhat higher in the North Atlantic basin, parts of the North Atlantic, than it would be if the Greenland ice sheet weren't there. As the ice sheet starts to melt, its gravitational attraction is reduced because the mass is reduced, and that force relaxes, and some of that water sloshes backward into the rest of the ocean. That causes a local effect. It's not just when you take some ice off Greenland that you put it in the ocean uniformly. There's also a local effect with a disproportionate effect in the northern hemisphere, which is counter to the increase in sea level rise that occurs due to putting the ice in the ocean. You increase sea level rise in the North Atlantic a little bit by putting ice in the ocean, then you decrease it by that bulge of water that had been situated near Greenland, relaxing back into the rest of the ocean. And that complication is the opposite for Antarctica. If you lose ice off Antarctica, you relax a bulge which otherwise would exist in the South Pacific. There are other local effects like that. When you add them all together, it becomes damn complicated to try to actually calculate what future sea level rise will be at any one location, particularly since we don't understand the relative contribution in the future to sea level rise from Greenland and Antarctica. We don't know which ice sheet and by how much will disintegrate, and so it's hard for us to project what will happen in any one location. It's easier, but it's still not very easy to try to guess what the global average sea level rise will be. Don't try to read this graph. It's really to jog my memory than anything else. One other source of information about the ice sheets is that we can look back at past climates when Earth was about as warm as it's going to be in this century. And the last time it was that warm was a period called the last interglacial, about 125,000 years ago. And there is now some pretty good evidence from a study that I did with my colleagues that sea level did rise by at least 6.5 meters during that period compared to today at a very relatively rapid rates, periods where it rose by an amount which translated into century scale would be about 0.5 to 1 meter per century, which is fast to try to adapt to. And the main point is, though, it looks like both ice sheets made about a comparable contribution to the sea level rise, although we're not sure about that. That's the least sure part of this study. So it looks like there is a real threat that not only one, but possibly both ice sheets will make a significant contribution to sea level rise in the future. What's uncertain is when it will be triggered, whether we have to go into several hundred years of warming before this starts to happen, or whether it happens immediately or may indeed have started. We don't know the induction time. We do know essentially the temperatures during that period were no different likely than they're going to be in the middle to late part of the century, although for different reasons than the buildup of the greenhouse gases. So putting all this information together, many scientists have been struggling with how to add in what IPCC chose not to, that is, how bad could the situation be? And there have been several studies done since the 2007 IPCC report, including one that was commissioned by the Dutch government, by the Delta Committee of the Dutch government, and which I participated in, and several other people in the room did too. And in that study, the global that's what this chart shows here. We estimated sea level rise to 2100 and 2200 due to the ice sheet and other contributions. And this is, again, is the upper bound. This is how bad could it get. This isn't what's the median or what's the range. Global sea level rise the upper band of global sea level rise is estimated to range from about 0.5 to about 1.2 meters by 2100 and 1.5 to 3.5 meters by 2200. That's a huge uncertainty, especially by 2200. But along the Dutch coast, the situation is even worse, with this gravitational effect playing havoc with the old way of doing it, of just looking at the global mean. And there's a very large uncertainty for the Dutch coast, ranging from a relatively small sea level rise comparable to or even smaller than the IPCC lower limit of 0.2 meters, right up to over a meter in 2100. And for 2200, again, the numbers range from very small to something like 3.5 meters. Other estimates of the upper bound by 2100 actually reach 2 meters, and this ties back to the point I made at the beginning. that table I showed of 8.7 million people potentially displaced and 5% of the 40 deltas being inundated, well, that was, again, remember, for a 2 millimeter per year sea level rise. If sea level rise reached 1 or 2 meters in this century, we'd be talking about rates of 5 to